Hello. Today we're going to go over partial pressures of gases. And one thing we need to realize is that every gas exerts a pressure based on its volume, amount, and its temperature. If there's more than one gas in a container, each gas has its own pressure. And the total pressure is equal to the sum of all individual pressures. And for us, that means that the total pressure is equal to any gases that we have there. So for gas 1, 2, 3, and so on, we just add their individual pressures together to get a total. So let's look at a problem. Here we've got two bulbs that are connected by some sort of cylinder that we're going to consider has no volume. The volume on the left-hand side is half a liter, and it contains 0.75 moles of oxygen. The volume on the right-hand side is 0.25 liters, and it contains 1.25 moles of nitrogen. The whole thing has a temperature of 298 Kelvin, so we want to figure out what's the partial pressure of nitrogen and oxygen and the new total pressure when the barrier is removed. So things to think about before we begin, after panicking of course, include when is the barrier removed? What's the new volume? Can the pressure of oxygen be determined? And since we have moles, a new volume, and a temperature, the answer is going to be yes. Can the pressure of nitrogen be determined? Just the same for oxygen, yes. And what is the new total pressure? So each of these little sub-questions will lead us to our final answer. So let's look at the new volume first. So we're going to have one volume that is 0.25 liters being added to a volume of half a liter, coming out to a total volume of 0.75 liters. When that little stopcock is removed, that's when the new volume becomes 0.75 liters. Now, how do we get the pressure of oxygen? Well, we're going to use the ideal gas law. And we rearrange it so that the pressure of oxygen is all we're really interested in. And we plug in the things that we know, which is 0.75 moles of it. And the ideal gas law constant multiplied by the temperature divided by the volume comes out to 24.4 atmospheres. Now let's do the same thing for nitrogen. Again, the new volume is 0.75 liters. So the pressure of nitrogen we can get from the ideal gas law, which we've rearranged to include just the pressure for nitrogen. Plugging in the things that we know, 1.25 moles multiplied by the same gas constant and the same temperature and divided by the same volume gives us 40.8 atmospheres. The thing to realize here is that the pressure here goes up largely because we have more moles of nitrogen. Now, the total pressure, that is going to be equal to the sum of the individual pressures. Nitrogen and oxygen, they add up to be 40.8 and 24.4, coming out to 65.2 atmospheres. And that is the final answer that we're looking for. So what are some things to think about here? Well, we use PV equals nRT. It's the best equation of state we have. Try to remember what changes and what stays constant when you're looking at these problems. And remember that these pressures are additive, so that the total pressure is equal to the sum of the individual pressures. So with that in mind, let's try this. You've got 0.75 moles of methane reacting with excess oxygen at 425 Kelvin in a 50-liter container. When this is done, what is the partial pressure of carbon dioxide and water, and what is the new total pressure? So there is your unbalanced chemical reaction. And now, if you did this properly, you will get a partial pressure for CO2 of 0.523 atmospheres, a partial pressure of water of 1.05 atmospheres, and a total pressure of 1.57 atmospheres. Thanks for listening. We'll see you in class.